Hi, I'm Steven, and I will be starting our group's presentation, and our project was a Rubik's Cube solver. The goal of our group's senior project is to build and program a mechanical setup that can manipulate and solve a 3x3 Rubik's Cube in 5 minutes or less, and to act as an exhibit piece for our major at student recruiting events. It is also meant to display some of the skills we learned here in the ESET program, such as 3D CAD drawings in SolidWorks, electrical circuitry, and programming. We also had optional features planned that we would add if time permitted, such as an automated randomized cube scramble where the machine would randomize the cube for it to solve. We also thought it would be cool to connect a tablet and program a GUI that would display code as it is running and be able to send commands to the machine by touching the screen. Why this design? From the start, we wanted to find a project that would be interesting to watch in action. While there are simpler Rubik's Cube solvers out there, we decided to use the design we found on Instructables.com called ARS Arduino Rubik's Solver, posted by Super Mario Professor. The main reason we chose this design is most of the structures are made of acrylic, and there are many mechanical moving parts which would make it interesting to watch as it solves the cube. This project also had some documentation available online, such as the files needed to cut the acrylic pieces readily available, a collection of some of the algorithm code that would be used, and a list of materials needed. The drawbacks of this design is the original project was made at a university in Italy, so the instructions were mainly in Italian and it was difficult to understand and translate. Another is that the pieces are made out of laser cut acrylic, so it's going to cost more in financing than other designs, and also because of all the moving parts we're going to have to spend more time on testing. While we did have the laser cutting files, we had to make all of the engineering drawings and 3D models ourselves. We used SolidWorks CAD software to make the drawings and models, and we also made assembly files to check for clearances and to make sure everything would fit together as intended. In total, we had 29 individual acrylic pieces to model. We also used SolidWorks to redesign the mount for the camera. For the assembly of our project, we had a custom stained and scored baseboard, 100 individual acrylic pieces, custom fabricated metal rods with tapped ends, 3D printed pieces for the mechanical belts, cube manipulators, and camera mount, and it took about 40 hours to assemble all together. The biggest delay we found was that the acrylic used in the original project was in metric thicknesses, and to get those type of thicknesses in the US would be a significant increase in cost. We decided to alter the design to fit imperial thicknesses that is readily available at places such as Home Depot. This slowed down productivity because each piece needed to be altered in SolidWorks and checked for accuracy. This redesign delayed the project 2 weeks. Once the CAD files were changed and the acrylic sheets had arrived, we had the acrylic laser cut at a local shop. It took about a week turnaround. Once we started to put everything together, we found out that there were missing pieces and had to make a second order for laser cutting. During the second order, there was a mistake in one of the files where the units had changed from centimeters to inches and caused a dimension problem for the cut piece. The lesson learned is to always check units before sending files for fabrication. The top piece in the picture to the right is the correct size. The Sharpie pen is for scale. In our project, there are 4 8x572mm shafts that hold up the motor structures that manipulate the cube. The problem we ran into with these rods is they are tapped at the end so they can be held in place. Turns out that buying custom shafts with tapped ends is very costly. Luckily, Julian is an experienced metal fabricator and had access to a metal lathe to tap the ends, but this added a few weeks delay for construction. We had to modify the design a few times as we were putting it together. For all the sliding motor chassis, we found that they were unstable with just a force fit. We ended up using some extra acrylic as washers and drilled out holes for screws. This solidified the chassis and solved our problem. Another modification we had to make to our original design was to the 3D printed cube grippers. The opening was too small to slide onto the shafts of the motors, so we drilled out the gripper and added a set screw to the side to hold it in place. Also, in the original design, it called for fans for the motors that rotate the cube, but we had to omit them. The reason being is the motors that we used were longer than the ones used in the original design, and the fans would not fit in the space behind the motor. We also had to modify the motor box housing. The motors we used had a little lip that sticks out just enough to keep the motor box roof from fitting all the way into place, so we drilled out an opening in the roof using a Dremel tool.
Hello, I am Julian Bustamante, and I will be picking up where Stephen left off from. Another change in the designs that we had coming from the original Italian was the camera. We decided to drop their fixed camera mounted to a plate that would overlook the Rubik's Cube solver entirely. We decided instead to go for a Pixie Camera. This meant that we had to come up with our own design from the ground up. Though we did keep the original rods that were used to hold up the mounting plate for design convenience. This would come up in two parts, a box that would hold the Pixie Camera and a spanner to go across the rods. The Pixie Camera case came in two parts, a top and a bottom. The top plate would hold the Pixie Camera via three holes that would be tapped, using the three holes that were already on the Pixie Camera as through holes. This would also affect the design of the box, in that we would be using a 3D printer, a MakerBot 2, to print out the case and spanner. This also provided a design challenge in that 3D printers may not have proper tolerances to hold tap holes. So what we did was we made the tap holes smaller, even though the MakerBot 2 has a precision of 0.02 millimeters in creation. But we didn't want to risk this, so we made the tap holes smaller to ensure that we would have, regardless, strong tap holes that would have enough room for threads to hold the bolts. And this was proven correctly, in that our tap holes were made very precisely and had enough strength in them to hold the bolts and the plate together. The spanner bar came in three parts. Well, two actually, but the spanner bar involved the bar itself and the caps that were designed for it. This was designed to be adjustable to all points along the rods, not just the very top of it, like the original mounting plate had. This was because we would friction hold the spanner to the two rods via a cap that would vise in on it when you would turn two bolts at each end. This will allow for versatility and height for the camera to be mounted to, unlike the original design.
Hello, my name is Jesus Hernandez, and I am the software lead on this project, and today I'll be taking you through the program flow. I'm more or less just going to go over the state machine and some challenges that we faced. So just a simple walkthrough the state machine. We start at an init state, go to idle, get cube state, check if the cube is solved, if so return to idle, if not pass on to the Rubik's Cube algorithm, perform the solve, and return to idle. So what we do in init and idle, init will instantiate all the variables, the motor objects, the link to the Pixie Cam, and set up the low-level drivers, which will be the GPIO of the Raspberry Pi. The idle state is just idle, it's as named. This is go between state to wait on a new cube to be inserted so that we can restart the process. Now the cube solve decision block. How this is accomplished is that the Pixie Cam will go and select 9 locations within the frame, which will be dependent on where the squares of each face are at, and we'll grab the RGB color value of each square, and we'll do this for each side of the cube. We'll rotate the motors because our camera is on a fixed mount, and we'll map it to this output as shown in the image to the left of the bullet points. And we'll check, do a simple error check, see that we got 9 of each color. That way we know that whether or not to rescan the cube, because there's only 6 sides and each side is one color with 9 pieces on it. And then we format that as we go to we format that output to match the input of our Rubik's Cube solver algorithm. And if it is solved, great, we'll go back to idle. If not, we'll continue with the Rubik's Cube algorithm. Now the solve we interpret the output of the algorithm. The algorithm itself was grabbed from a Python module from the PyPy index. I'll link to that in the end of the credits slide. But the output is basically a string given the sequence that should be followed in what's known as the Rubik's Cube notation. So in the solve, we map the notation to certain motor movements such that they coordinate. So a front clockwise rotation will turn the front facing motor clockwise 90 degrees or 180 degrees if it's a front 2 or F2, F prime. The primes indicate counterclockwise rotations and so on, things like that. The full details about the cube notation are in the link on the 4th bullet point, and we'll just go through the string until we reach the end of it and execute each rotation based on what the string tells us to do. Once the sequence is finished, we'll return to idle, and since we periodically check, the system can self-verify the cube at that stage. So the overall program structure is broken up into 3 tasks. These represent the 3 branches that I used on GitHub. There was the camera task, the motor configuration task, and the mapping the camera output to the cube rotations. There may be more branches on GitHub for minor things, but these are the 3 main branches that were worked on. The camera needed to acquire color from frames, and that required getting familiar with the Pixie Cam API. And we needed the fixture and lighting setup such that we can create a tolerance for color ranges. If you don't have consistent lighting, any calibration or tolerances go out the window, so we really needed that to be fixed. The other task was motor configuration, which configuring the motors to work with the stepper drivers, driving the I/O to step, and keeping keeping track of the current position in software with a variable counter. The reason we need to do that one is because there are certain rotations that might lock up if 2 motors on adjacent sides are one's at, let's say, at 0 degrees and the other one's at a 90 degree rotation. They will lock up if one tries to turn, and we needed to account for that. So the easiest way to do that without a feedback system is just to have a software counter, and we can check for any we can look ahead to see that, hey, this operation will result in a lockup. Let's reset that motor back to home position. Mapping camera outputs to cube rotations is the final task, and that was taking the RGB values, putting them in an array that'll fit the format that the Rubik's Cube algorithm will take, and then taking a step further and taking the output of that algorithm and mapping it to rotations. So we did this by having a Rubik's Cube solver object. There is this particular function to take the output of the algorithm and map it in such a way that the Rubik's Cube solver object would understand it and translate it into cube rotations. The motor itself is its own object, and we wanted that to be abstracted from the Rubik's Cube solver so that it could be reused in other projects. So some challenges faced while we were developing. Our design is open loop. We do not have a feedback system. This is an issue for us because of, again, the motor position relative to the others. So let's say, again, the lockup issue that I mentioned before. If we had a limit switch such that we could home in onto what would be like the 90 degree or the 0 degree position, then it wouldn't be as much of an issue. But timing didn't allow for that. Also, one thing with the open loop design is that we can misstep, which a misstep, maybe we drop 1 or 2 steps. We're not micro-stepping our steppers, but the hardware design isn't fixed perfectly onto the cube, so it doesn't turn fully. While the motor might do 90 degrees, the cube might only do 89 or 86 degrees because of the tolerance on the grippers, which will create lockup, because if it's not flush or if not close to flush, the cube won't rotate. And that leads into mechanical issues, is that the cube grippers weren't tight enough, and as a result the cube may not do a full rotation, which will in turn lock up our cube. Now, a proposed solution to that would be to tighten up the tolerances on the gripper fitting, or use a limit switch so that we can reset and account for lockups, or tackle lockups as fault states when they happen. Some further challenges, some software delays. The delays in hardware push back the software development cycle. Without the physical hardware in front of you, it's very difficult to try to plan for the elements that are very hardware dependent. The lighting fixture was the most glaring issue. I tried to abstract that as much as possible without the actual pictures and frames and the RGB values available. So what I did was I took a cube and I manually entered in the values, and I wrote the interpretation of each colors. The values will change later on the frame when the frame is available, but I passed those to the Rubik's Cube solver algorithm and had the output interpreted and passed to the Rubik's Cube object. Now, now not having the frame also meant I didn't have the motors in front of me for quite some time, and there was a fair amount of debugging with that, because I had to visualize how the motors would work in tandem with each other. So the more complex movements, like maybe doing a rotation on the top of the cube, were rather challenging to think about without the hardware in front of you to at least turn an actual cube, or at least watch the rotations. So once I got the hardware in front of me, I had to debug that for at least a week. And working remotely as of the circumstances kind of prevented a little bit of team communication, which is a challenging issue. If we had given, different circumstances, I'm sure these wouldn't have been problems, and we could much quickly address other hardware challenges that were drawbacks, such as like one of the gripper mounts breaking, or the tolerances on the grippers, or some kind of fixed frame for the camera. And these were some of the challenges we faced in the software development.
Thank you for watching our presentation at this year's Cal Poly Pomona Senior Symposium. As we close out, here are some pictures of the construction progression and the finished project.